cubic is in many ways similar to a quadratic, except it's, well, a terrible joke, but it's the 70s dance move of the function family. It does this or that, as opposed to that, alright? Yes. Oh yes, all day. Now, it has the most basic form of y equals x cubed, alright? And that's the form that we build on when we want to start graphing cubics. So similarly how we started with y equals x squared with quadratics and then learned how to transform it and what adjusted that x squared, similarly we do the same with x cubed. Our first transformation or different form is x take h all cubed plus k. We use h and k exactly the same way as quadratics. In quadratics that adjusts our vertex or turning point. Cubics don't have a vertex exactly. They have this point here, and that blue line is x cubed. That red line is just meant to be me trying to draw x cubed but transformed up and across. That point there is called a stationary point of inflection, and it comes on later on down in the notes, so don't worry. Now, this transforms the point of inflection h to the left and k up. If we put an a in front here, what did that do with quadratics? What is the effect of the a in a quadratic? Yep, shape and concavity or convexity for quadratics. Similarly with cubics, it's shape, whether it's really, really narrow or spread out, and instead of concavity and convexity, it changes from this to this. Okay? That's the A. When the sign changes on the A, it changes like this. The reason being, if you cube a negative number, you get a very large negative number. If you cube a positive number, you get a large positive number going this way. However, if the sign's different, the entire thing gets flipped. So basically, you're cubing a negative, which gets you down here, but the minus A starts up here. Alright? So a negative A would give you a quadratic that looks something along the lines of this. Yes, terrible. This is why we use either your graph paper or calculators to do it. And we will be using calculators a fair bit. But that's the effect A has. And essentially, a really low A, so A of a half, or a quarter or something less than that, will look, if this is negative a third, and then negative 3 will be much steeper. But the point of inflection will be the same. Okay? Just like with a quadratic, your turning point will be the same, it would just be steeper or sharper around that point. Alright, so point of inflection is when the function changes from concave to convex, or vice versa. Convex, concave. And you're all familiar with concave and convex? Concave is the little man in the cave. So this part here is concave, and that part there is convex. Now, below is a more typical sort of cubic function. Its point of inflection is here, about where the function changes from concave to convex. And we use a slightly different terminology depending whether it looks like this or the function above, like that. This is called a stationary point of inflection, and this definition becomes more useful when you do calculus. But stationary point of inflection because at that point, the slope of the line, the slope of the cubic is 0. Whereas with a non-stationary point of inflection, it simply goes from concave to convex, and the slope of that line isn't necessarily 0 there. That's the difference between the two. We're talking terminology-wise. Alright, so if you were asked to graph this function, or make a sketch of it without using your calculator, you start from the basic, that is y equals x cubed. The point of inflection is transformed across 3 up 4, and because of the 2 out the front, it's steeper. The whole thing should be steeper. And if we're going to show that on the calculator, you guys can graph it as well while I'm doing it. X to the power of 3. Alright, so that blue line is the standard one, and the red shows the transformation and the narrowing of it. If we wanted to show the effect that different A would have, we could write -2 and repeat the same function, and it should have the same inflection point, simply a different orientation. And how do we find the y-intercept of that?
When x equals 0.
Yeah, when x equals 0. So when x equals 0, you get -3 cubed, which is -27, times 2, -54, plus 4, -50. So this will cross the y-axis at -50. Yeah? So, same rules apply to quadratics, apply to cubics, and then will apply to quartics. Right? And on that note, we will sometimes ask you to put functions like this in general form. General form being ax to the power of 3 plus bx to the power of 2 plus cx plus d with a not equal to 0. Alright? How would you go about that, getting that in general form? Expand and simplify? Huh? Use what? Yeah, so if you remember Pascal's expansion, with Pascal's triangle, you can use that. If not, just write this as x take 3 squared by x take 3, expand out the quadratic, and then multiply it by the linear. Alright, and remember that that 2 stays out the front and will eventually multiply through the entire thing with a 4 at the back. Alright? Now, please do note the cube in the test. There was, I know, a fairly vicious imaginary cubed question. Lots of people just wrote it down as a squared. Alright? So please remember to cube it out in the test, yeah. Question 1.
Did you notice the way I did it? The Pascal's expansion.
Yeah.
Just like that, too.
Alright. What's Pascal's expansion? Alright. Basically, sure. No, nice shortcut. Alright, so if you have a plus b to the 3, Pascal's triangle says you get a to the 3 plus, now what's the next coefficient, is it 3?
Yep.
3a squared b plus 3ab squared plus b to the 3. Essentially, you'll notice the power of b decreases each time. So the power of b in this term is b to the 0, which is 1. Then you've got b to the 1, b to the 2, b to the 3.
That increases.
Increases. Sorry, the power of a decreases. So it starts off with 3, goes to 2, goes to 1, then is 0 here. Yeah. Again, it's not something you need to memorize. It is a cool trick if you know it and are comfortable using it. If not, you'll have to do the long expansion. Yes. It'll be... Huh? The a cubed would still be positive though. Yeah. Then minus.
I guess plus minus.
Yeah, plus. Yeah, the sort of thing alternates. The sign alternates. Alright, as with quadratics, we have an axis-intercept form. Essentially, it's a quadratic axis-intercept form, but with an extra intercept possible. Alright, and once again, I've done what you guys do. I've forgotten that a cannot equal 0. How is that possibly that? Not equal 0. Insert. Thank you. Alright. So for this, the three intercepts would be alpha, beta, and gamma. Just like in quadratics, if we had two intercepts, they'd be alpha and beta. Now your folio task is essentially an exploration of this sort of form and the other forms of a cubic, and then quartic. What you'll notice, or what you can think about, is a cubic is made up of essentially a quadratic and a linear. And this is, without going into too much detail because you'll explore it in detail in your folio, this gives you a couple of different possibilities. Either you can have just a single root, that being the point of inflection, or you can have a single root and two imaginary roots. So for example, sorry that's going to go off the screen, that red line there has a single root and two imaginary roots, which would mean the quadratic component, so if that represents our single root, the quadratic component must have a discriminant of less than 0 for the other two roots to be imaginary. If this doesn't make entire sense now, don't stress too much, because you'll go through step by step in your folio and nothing out then. Folio's good fun. I thought it was the week after. Folio draft due Friday, not next week, the week after. Yeah. Alright. And on that note, next week I will see you on Tuesday. Then I am away Wednesday, Thursday, Friday. I will record lessons and teach you via YouTube, and on Friday the plan had work on folio anyway. So you'll just have one YouTube lesson to make sure you don't fall behind. Alright? I know it's not particularly fun or the best way to teach, but at least it means we can go through the material at the same pace. Alright, so huh?
Is there a way to factorize
Factorize those three cells? No. Make the first two into a... What do you mean, factorize or simplify?
X take alpha, X take beta.
We'll go to that. So what happens is, if you're told that... Alright. So, Josh's question was, if you have a cubic, say, x of 3 plus 2x squared plus 7x minus 6, can you factorize that easily into the form of y equals a x take alpha, x take beta, x take gamma? Now, if you put this into your calculator and it comes out as 3 real roots, then fantastic, happy days, you have alpha, beta, gamma. Alright? What's equally likely is if you put in your calculator and come out as 1 real root, then this is what you have. You have y equals a, and then in here is a quadratic, and if you found the 1 real root, because cubics always have 1 real root, say that real root's 3, you'll have x take 3. Alright? And what you're still missing is the quadratic here. If you like, you can put in the quadratic as x squared plus bx plus c. Now we will go through this in more detail later because I wasn't planning to do it this lesson. But what you need to do then is expand this out, etc. You'll end up with 6 terms, collect like terms, and then you can equate coefficients. So, by that I mean if you have this function is equal to ax3 plus bx squared plus cx plus d, then we can say that a is 1, b is 2, c is 7, d is minus 6. So if you wanted to find this here exactly, you'd have to expand it out, expand all of this out, and then you'd have something to do with ax cubed. You'd have a coefficient of x cubed, and that coefficient of x cubed would equal 1. So you might end up with a term like a plus 2b x cubed, when you take out a common factor of x cubed out of that, plus b plus 3c x squared. So take, just another plus, a plus b x plus whatever, plus, let's go 2c. And then we'd have to say that, alright, a plus 2b equals 1, b plus 3c equals 2, a take b equals 7, and 2c equals minus 6. Okay? It's similar to saying a plus bi and then equating the real part and the imaginary part. So you know how you take out the factor of the real parts and then the coefficient of the imaginaries, and those are equal? Here, you're not looking for real or imaginary, rational or irrational. You're looking for the coefficients of the corresponding x powers. So you're looking for the coefficients of x cubed, and the coefficients of x cubed will be equal. You're looking for the coefficient of x squared, and they'll be equal. It's essentially like simultaneous equations, except you have 3 unknowns. But the good news is you get 3 or 4 equations out of it. Because that's 1, that'll be 2, that'll be 3, and that'll be 4. Yeah?
Is it confident at the end of this period? The confident at the end, you've got 2c there, isn't it? So you've got that
Yeah. But if you expanded this out, your constant term would be like AAC minus 3AC. I just made these numbers up. And then you could say minus 3AC equals minus 6. Yeah. Alright, but that isn't actually today's work. That we'll get to later when you've done some more playing with cubics. Yeah, it would take forever, but they're good marks. Can you look at these questions? It's essentially graphing and practicing sketching graphs. Do question 1 all on the same axis to save you drawing lots of different axes. Just make it nice and big and label your cubics clearly. Then those other 2 questions and the odds of them.